Good morning, everyone. We're officially starting the second day of our Quantum Nurse Days. Thank you for being here, especially so early. If you want more coffee, it's always available. Our first speaker from today is Mao Lin from AWS, and I'm talking about a partnership with a project with Quera, I believe, and other researchers. So please take it.
Yeah, thank you. Thank you. Thank you, the organization, for the invitation to having me here. So today I'm going to talk about work done. I'm not sure which one is. Yeah, just look at here. So the work done on Quera device using Rydberg atom to simulate a lattice called Shastry-Sutherland lattice. So this is work with lots of collaborators from 4 organizations: Quera, Purdue, Amazon Brack, and Oak Ridge National Lab. I will point out that Milan and Fang Li from Quera and Baohan from Purdue are the main driver of this project. So basically, this work will not be possible without their effort. This is the outline of the talk. I guess most of you haven't heard about this lattice. I haven't heard about it before this project, so I'll introduce that briefly, in particular classical model. And I'll show you that it's interesting to study because it's related to some real materials. And then I'll move on to talk about the quantum version of the lattice, in particular in the context of Rydberg atoms. And I'll move on to show you some experimental results, and I'll end with a brief introduction of Amazon bracket on which this work was carried out. If you forget about what I'm gonna say for the rest of the talk. So the main takeaway is that this lattice is interesting to study because it's relevant to real materials. And we discover a couple of new phases that that is unique to the quantum version of the lattice. So let me just introduce the lattice. So this lattice was originally defined on a square lattice shown here. So J1, J2, J3, so J1 is the nearest neighbor interaction shown here, and J2 is the blue bound here. And just notice that it's not all the next nearest neighbors interactions will include only this blue bound here. So for example, this one is not included, and J3 you can forget about. Actually, I mean, this is not really relevant for the rest of the talk, but I just want to add it here so that because it has been exactly solved even with J3 included. So in this classical model here, sigma z is defined as plus and minus 1. So I just show you the different phases in the classical version of the model. So this one was exactly solved in the second reference here. So here I show the phase diagram when J1 is bigger than 0. But when J1 is smaller than 0, basically you don't have the third and the fourth phase here, and then phase diagram just collapses to a few phases with Ising dimer and ferromagnetic phase. So what I'm gonna do for the next few slides to introduce these phases to get prepare to understand this phase diagram here. So sorry, the first phase is quite easy to understand. So when H is I forgot to mention, H is a longitudinal magnetic field, and if it is really large, then you can expect that all the spins are in either point up or point down. So that is ferromagnetic phase here. And for the second phase, so-called Ising dimer phase, you can also understand similarly by taking J2 to infinity and H to 0, then you can expect that this dimer will have spin up and spin down, right? So that is what is shown here, and that is the same for all the dimers in this lattice here. So you can see this kind of configuration here where each dimer has black and white dots, right? And this one has the ground state degeneracy is to the power of system size because each dimer is independent. This is the second phase called Ising dimer phase, and the third phase is the Neal phase, and you can similarly understand it in the following way. You can take, let's say, H. You can think of it as when J2 is very large, then all the dimers tend to be the same value, plus 1 and plus 1, both plus 1 and both minus 1. But because H is because J1 is bigger than 0, so the nearest neighbor tends to be opposite to each other. So in general, you look at it, you can figure out the configuration looks like plus minus with this kind of Neal configuration. So yeah, this is a new phase. So people have understood this three phases even before people actually was able to solve this model exactly. And there were some, doubts whether it's a different phase that has not been discovered. That is a one-third phase here. And it was only confirmed when, people found the exact solution of this phase. And it looks at the following way. I wasn't able to fully understand the solution, but I just want to, display the configuration here. So the way to think about it is that you have a stripe of, anti-Fermi order, plus minus, and then a different kind of flip the sign in this layer here, minus plus, for example, and followed by a Fermi layer. So all the column here have the same spin value, and then you repeat this pattern, right? And you can calculate this average minimization to be 1/3, and that's why the name is called one-third phase here. So okay, so we take this, this few slides to introduce the phase diagram here. And you may say, hey, well, why we're interested in this one? I mean, this looks very neat, but what's the relevance of that, right? So, and the point is that there are several families of materials that have very similar structures. So here I show you one examples here. So this this material looks at the following way here, and it doesn't quite look like square lattice. But suppose you deform this lattice to the following way, you can kind of just look at it and see that this topology is really the same as square lattice shown here. And then you can see that this one is actually quite similar to the one here. And people actually was able to confirm some of the result they calculate on this model using some experimental method, for example, neutron scattering, to confirm some of the results here. And yeah, this is another material that is relevant to this model here. Okay, so because of the relevance to real materials, so people have actually simulated this one on D-Wave. So this is one of the results they want to display. This is actually done recently. So they were able to map out the phase diagram that I just showed you in this model. So they were able to find dimer phase, new phase, and this particularly is a 1/3 phase. Okay, they were able to confirm that indeed this model has this 1/3 phase. So I would like to show you, let's just show you some of the results in that paper. So you can see here, this is one of the new phase. You can see this alternating patterns between rows and columns. And more interesting, they were able to see this pattern with, let's say, anti-Fermi column here and here, and then you have the third column that has the same spin there. So this is a 1/3 phase. And to actually characterize this phases, they use this so-called structure factors. Basically, it was a two-point correlation function, and then you do the Fourier transform, right? And for the new phase, this structure factor has a peak at pi value here. And the 1/3 phase is a different characteristic. So you have the peaks in the 1/3 times 2 pi, and the mirror symmetric point as well in the Brillouin zone, so to say there. Okay. Yeah, so we actually use a similar, actually the same structure factors to characterize the phases in our experiment. Okay, so the midpoint summary. Yeah, one more. The midpoint summary. So is that the lattice is relevant to several materials. So but it seems that the phase diagram has been well understood. So what's the point? Is there anything new that we can do? And the answer is yes. So let me just show that now. Let me just move a little bit faster. Okay, yeah. So I think it's too busy. So so I already show you the classical models, which is here. So to study the model in Rydberg atom device, we just redefine this model in the following way. So we make this transformation, and now this part is the classical model that we just talked about. And now we add one more term, that is the omega divided by 2 term here. That is a driving term that drive each atom. So by the way, each atom is two-level system with ground state and Rydberg state. And this omega divided by 2 term is driving the transition from ground to Rydberg state. And the Rydberg, the Hamiltonian defined lattice looks at the following way. As I told you, it was originally defined on the square lattice, but now here we're focusing on this kind of little bit tilted lattice as shown there. And the reason was that the way we realize this V1, V2, V3 is through the Rydberg interaction. And the Rydberg interaction actually depends on the atom distances as shown here. And by tuning the atom position here, we can actually tune the V1, V2, V3, which allowed us to explore the phase diagram of the lattice. Right, so here is the result that we want to highlight. So we do a DMRG simulation for this model with omega non-zero. And then we define, because of, we have one more parameters here. So we have a third parameter to explore, which we call RB1 here. That is the ratio between the nearest neighbor interaction and omega to the power 1/6. And when this one is non-zero, we calculate the entanglement entropy, and we see that there are several phases here. So this is the 1/3 phase that we have seen in the classical phase, and this is a new phase, and the new phase, sorry, the not old phase, is the 2/5 and the 4/5 phase that is in the boundary between the new phase and the 1/3 phase there. So we're pretty happy. We're pretty excited to see that, because this is something that is not seen in a classical phase diagram, as we showed here, right? So and there's one more phase that is new as well, which is a quantum dimer phase that is kind of resemble to the valence bond phase, for example. So yeah, so we saw these new phases, and then we want to confirm them on the Rydberg device. Okay, so yeah, so let me just show you some more results in the of the different phases. So this simulation is done using the DMRG with the geometry looks like this. So this is cylindrical geometry where the y direction is periodic, the x direction is open. So here we pick the parameter in the new phase, and then we calculate, we do a DMRG simulation, we find the ground state, which is shown here, and then we calculate two-point correlation function, and then we do a Fourier transform, as we have seen in the other paper. And then we see these peaks here, which is peaks at the pi point there, corresponding to the new phase that we have seen, and we kind of expect from a classical phase diagram too. Let's see if one more thing. Sorry, one more thing is that you can see there's some peaks also in the 0, Q equal to 0, there. That is due to the some artifact in the definition here. So if you actually calculate the structure factors using this formula here, you won't see this peaks here. I think this peak is calculated with Ni and Nj correlations. So yeah, if you actually use this new formula, you won't be able to see this peaks here. Yeah, so we actually move on to calculate similar thing for the 1/3 phase, and we can see that again, you have, let me try to see here. Yeah, again, you can see this alternating patterns in the first two columns here, followed by a column with uniform Rydberg density in the third column, and then you repeat this pattern like that. And if you actually do the Fourier transform, you can see the peaks located in the 1/3 times 2 pi peaks there, which is confirming the fact there's a 1/3 phase here. And one thing to point out is that in the previous plot, if you remember, the plot from the D-Wave paper, they have 4 peaks, right? One is 2 are located in this position, and the other 2 is the y direction here. And the reason we don't see there is because we actually don't have an infinite system here when we are having a cylindrical system. We actually have a cylindrical system, and then y is actually much. It's actually not that much to see the peaks in the y direction. But actually, if you extend the system to y direction as well, you should be able to see the 4 peaks as we have seen in the other experiment. Yeah, so this is 2/5 phase. This is something new that we want to highlight. So if you actually pick the parameters in this very tiny regime here, you can see that there's 4 alternating columns here, followed by a column that has more uniform Rydberg densities. So that is what we label as a 2/5 phase in this material. And I think I didn't actually emphasize that, suppose I mean this phase is really stabilized by the quantum fluctuation induced by the non-zero omega term. And you can see that the fact that this Rydberg density is not either 1 or 0, there's partial value indicating that there is a superposition between different states in the pattern here. And you can also see there's a tiny peaks in the pi there. That is kind of remind you that original this region here is a new phase. So this is really a very closely related phase to the new phase, but it's actually have quantum origin. And the other phase that I want to mention is the quantum dimer phase that is up here. And if you calculate the same thing, you can see that there is a broad peak at pi zero position there. And in this phase, it's kind of very similar to valence bond state, where each point here is a position of the 1, 0, and 0, 1 state there. Okay. Okay, so yeah, so those, by the way, so those are simulation results. So we're gonna confirm that through one experiment, and just mention a few words on how to use the device. So the idea is that the delta and omega are time dependent, and a typical waveform looks like the following way. You prepare the so you start from initial state being where all the atoms are in the ground state, and then you tune delta from negative value to positive value at the same time. The omega is tuned from 0 and then down and then to a maximum value, and then gradually ramp down to 0 at the end here. And you may ask, right? So you may ask, the phase diagram that I just showed you depends on the fact that omega is non-zero, because we need the omega to be non-zero to stabilize the interesting quantum phase, I said 2/5 or 4/5 that we just say, which we just showed, right? But the fact that this one has to tune down to 0 seems to be problematic. But actually what you can do, as this paper or other paper has done, is that you can actually quickly ramp the omega down, like the one they show here. And like the system actually don't have time to actually, and then you do the measurement right here instead of, the label. Just do the measurement right there. So the system actually don't have time to respond to the fact that, omega has to ramp down to 0. So with such a trick, you can actually show that, you can pull the 2/5 phase, as we are gonna show now. Okay. And one more thing is that the simulation is always done on a cylindrical geometry. But in real device, it's always open boundary condition. So to stabilize the phase that we're trying to probe, we actually use another trick, which is to add some boundary atoms here, which are highlighted in red here, to actually stabilize the phase that we try to probe. For example, suppose I'm trying to probe the 1/3 phase, I'm going to add this 10 boundary atoms here to actually pin the phase that I want to see. If I'm trying to probe 2/5 phase, for example, I'm going to use a different set of boundary atoms. But the idea is that to avoid the finite size effect that is in the device, we're using boundary atoms to make the signal of the phase more stronger. Okay, yeah. So this is experimental results. So the left hand side that I show you is the simulation result, and then the right hand side that I show you is the experimental result. And here we're probing a region of phase diagram in this square here, and this one is measuring the 1/3 phase order parameters. And suppose I use the boundary atoms to pin the phase, to pin the 1/3 phase, then I can see a bigger region that shows that this region has a 1/3 phase. If I'm using a boundary pinning to pin the 2/5 phase, I see a region that looks like this. And if I don't do anything, you can see that the phase is actually less clear in this region here. I think the main message is that if you use the 1/3 phase to pin the phase, and if you see some finite region of the in the phase diagram, it actually shows that the system has that particular phase, but it can't actually show you the phase boundary in a very precise way. And also I should mention that this one is done on 14/6 systems, and the experiment is done I think in 8/9 system size. So system size is actually different as well. And you can't really compare the phase boundary between the experimental results as well as the simulation result here. Yeah, just repeat for the 2/5 phase, and we do actually a similar thing. actually we do the same experiment, but actually we just measure different order parameters at the end. And you can actually also see the 2-5 phase when you pin to the 2-5 phase here, and it's somehow more robust to the boundary effect. As you can see, if you pin it differently, it has showing the same order parameters in a similar region there, which basic this color bar? This one? Oh, this one here? Yeah, this one is order parameters. They actually didn't actually define before. It's a observable that we can post-process using the Rydberg density that we measure at the end. Okay, and we use that to distinguish 1/3 and 2/5 phase, and neo phase as well. Okay.
The experiment here is smaller.
Yes, if I remember right. Yeah, I think this is, let me see. Actually, it's done on, sorry, it's done using this geometry. Actually, 1, 2, 3, 4, 5, 6, 7. Yeah, 14/8. Oh, actually, it's similar. Yeah, 14/8. Okay, so it's comparable to the system size there. Okay, yeah. But I think what I'm trying to emphasize is that you can't really compare the phase boundary in the experiment to that in the simulation, because the boundary effect is very critical here. But we still can confirm that the phase is there, including the 1/3 phase and the 2/5 phase, as well as the new phase. And somehow some of the phases is more robust to boundary effect, and some, for example, 1/3 phase is not that. Yeah. And the last one is a dimer phase. So this is a simulation result that I showed previously, and the signature is that there's a ball band of peaks in the pi0 region, and we confirm that using experiment. You can see that in the pi0 region, there's a larger value of the structural factors there, and then the pattern seems to be qualitatively agreeing with each other, right? Okay, so yeah, this is the work in progress. So basically, I told you that omega, when omega is non-zero, you see this quantum fluctuation induced phase, which is 2/5 and 4/5 there. And I want to show that suppose you make this omega being smaller, corresponding to RB1 defined here to be bigger, then you should kind of have smaller region of these two phases, and gradually you should recover the classical phase, namely the collinear. A collinear phase is different than to the Ising dimer phase that I introduced in the first slides. And we're trying to confirm this one experimental, so it's still work in progress. Yeah, so this is the end of the kind of scientific part. So let me just introduce briefly Emmons bracket, where we did work. So Emmons bracket is allowing you to do research on using a bunch of different quantum computers. So here I kind of show you one example, which is done on Qurate device, but there are more devices on bracket. So basically, you can write and then test your programs in your local computer, and they can send it to the cloud, to the quantum computers on the cloud, and then run it, and then the result is sent back to you, and then you can post-process the results in your local computer. And there are several families of quantum computers online today. I've told you about the Qurate device, and there are a few more that we call gate-based device that can run quantum circuit. So one of the goal of bracket is actually allow you to easily run one program and write one program, and then run on different places, right? Like, suppose you have a quantum circuit, you want to run on different places, you can do it very easily. We try to make it easier to do that. But at the same time, we respect the fact that different QPUs have different characteristics. So we actually earlier this year we launched this program called Bracket Direct. So the purpose is actually to allow you to explore the new features in the device. So if there's a device that just come out from the lab, but it's not quite mature yet, but still someone would like to try it, we'll make it happen. So this is one of the purpose of the Bracket Direct program. And at the same time, you can connect to quantum specialist to actually, make the best use of the device, right? To avoid some caveat, for example. And also we have dedicated device, you have dedicated access to device through this program too. Just to highlight the one of the purpose of the program is to have the new features, that is not that mature, but still if you're curious about it, you can use it. So the one that I highlight here is for QRO device. We have 3 experimental features: local detuning, Hall geometry, as well as tight geometries. And so this is very useful in this particular project because this lattice that I show here actually has heights of 128 micrometers, and that is actually beyond the standard lattice geometry that we're allowed to run. But because it's so critical to the experiment, and then we launched this feature and allow people to use tall geometries, and also the row separation here is also smaller than the one that is we typically allow. And we have this tight geometry that allows you to realize more exotic geometries. Yeah, so that is all. So let me acknowledge my collaborators again. And if you want to learn more about brackets, there are some links there you can try to follow. Thank you.
Time for a couple of short questions. Yeah. Speak, whichever one.
So you briefly showed a plot that as you bring down the blockade radius and as you're increasing omega or decreasing omega.
Yeah.
The region of phases that are quantum stabilized by quantum fluctuations gets smaller.
Yeah.
You've done the opposite to see if those phases get bigger or if any more interesting phases show up in different fractions if you go in the other direction.
You mean omega getting bigger?
Yeah.
Yeah, omega getting bigger. I haven't tried that, but so the other thing is that there is a device constraint on how big omega can run. So I think what they're trying here is the largest allow in the device already.
But there's no constraint at the
There's no constraint of simulation. Yeah, I think people can try it. Yeah, we haven't done that.
So this is a perfect slide. I'm not sure I follow it, perhaps you can explain it. How do you get different V2 and V3 on the Rydberg atom system? Because if I understand the Rydberg interactions are isotropic, so how do you get two different for the sublattice IJ beta and IJ gamma? Two different V's for them?
Oh, yeah, so show it here. Oops. Sorry. Yeah. Oh, okay.
Maybe you can show the topology.
Yeah. I'm showing so this one. So the idea is you can tune the separation of this two to tune this V to become smaller and bigger. And at the same time, also you can also tune this one too. So they are not in the blockade region. Okay, if you're there, they are, then it's not quite.
Or you're outside the blockade?
It's in the intermediate region. There's still some finite interaction, but not really strong, not very small, depending on which phase you wanna pull here. No?
Could you say some words on the differences between the D-wave that you showed at the beginning and the simulations you're doing now?
Oh, yeah, so I think what D-Wave is doing is, I haven't personally used D-Wave, but I think what they're doing is that they just plug this Hamiltonian to D-Wave, and they can just find a ground state. And then that is basically simulating the classical phase diagram, because this is really classical Hamiltonian. And
you do the classical and the Kerr, and are they like similar sizes, similar fidelities?
we haven't done that, but suppose you want to do that, right? Then what you should do is, I'm trying to find what you should do is you should let this omega decay to zero much slower. Then you can see the classical phase diagram, right? On the other hand, we are trying not to pull the classical phase diagram. I'm trying to pull the quantum one, right? So you want this quench to, you want this decay to be really fast.
They can't do that on the D-wave, right?
I don't know. I don't know if they can do this kind of Hamiltonian. I don't know.
Ask a question, what are the lattice size differences? D-wave and what are?
Yeah, D-Wave, this one, I think, as I told you, this one is around 100 something qubits, and D-Wave, if I remember correctly, this one is 400 something qubits. So that's why they can see quite nice, for a transform in the different direction.
Thank you.
Okay, thank you.